Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing on with section 7.8, continuing our discussion and investigation of improper integrals. In the previous video, we introduced improper integrals of type 1, and we saw that improper integrals of type 1 were basically improper because their interval of integration, or the interval that you were trying to integrate over, was an infinitely sized interval. And what we were sort of tasked with doing is trying to understand which factor would sort of win out. The fact that we had an infinitely long region, or the fact that we had an infinitely thin or infinitely short sort of area that we were examining. And we saw that sometimes we could get finite areas, sometimes we could get infinite areas, but the main idea was that to actually analyze it, we had to look at it as a limit of a definite integral. In this section, or in this video, we're going to be continuing on in this section, but looking at improper integrals of a slightly different form. So instead of having infinities in the interval, in other words, instead of having infinite intervals, we're going to run into a different issue, but handle it in a very similar way. So just like before, we'll go ahead and take a look at a motivating example here. We'll consider the area underneath the curve y equals 1 over the square root of x, and above the x-axis on the interval 0 to 1. So what we want to know is this area finite or infinite? And if it is finite, what is its value? So once again, let's try to take a look at sort of a diagram of this. Now we're on a very condensed sort of interval. So I guess what we'll go ahead and do is maybe I'll label this as like 1/4, 1/2, 3/4, and 1. And then we can do this one as maybe 1, and 2, and 3, and 4, so on. All right, so we're looking at y equals 1 over root x. Now, if we think about that, like plugging in 1, we're going to get 1 over square root of 1, so I guess we have a point at like 1, 1 there. That's sort of going to be one end of the interval. Since this is a square root, it might be a good thing to plug in something like 1/4. Square root of 1/4 is 1/2. 1 divided by 1/2 is going to be 2, so I guess we have a point right there. And then, of course, we can't plug in 0 because we get 1 divided by 0. So what happens with this curve is that we're going to, if we sort of draw that in, it's going to sort of start to get larger and larger, and we would call what happens here a vertical asymptote, right? Because you can't actually get to x equals 0 because this is undefined at x equals 0, but as you get closer and closer to x equals 0, the curve just gets larger and larger. So the area that we're interested in is this sort of area in here. And you can see that in some ways, this is just a mirror image of the question that we were investigating with type 1s. Here, the interval is actually finite, so it's not an infinitely long interval. But what's happening is that in here, it's getting infinitely tall, right? If we sort of think about like an approximating rectangle, one of these approximating rectangles is getting very, very tall. But of course since this curve is getting closer and closer to its vertical asymptote, this is also getting very, very thin. The width is getting infinitesimally small. So once again, we have this sort of balancing act of which one of those is going to win out, and is this going to be a finite amount of area? So we're going to try a similar sort of trick to actually analyzing this. So we're going to, again, sort of imagine sort of cutting this at some arbitrary spot. So imagine we just sort of start here, and we look at t, and we say, okay, let's look at all this stuff here. And then we would slide that t this way. So if we think about that red area would, of course, just be a standard definite integral. The integral from that t value to 1 of this 1 over square root x dx. But then we want to slide t as close as we can to 0. So we could say that the blue area, and it should not be a surprise that the blue area is going to be based on a limit. We would say it's the limit as t approaches 0. Now we got to be careful here. Approaching 0, when we say limit t approaches 0, we actually mean from both sides. That's not the case here. In fact, we're only coming in from the above, things like 1/2, 1/4, 1/5, 1/6, whatever. So that means we're actually coming in from 0 plus. Remember, if you put the little plus here, you mean numbers very close to 0 but slightly larger than 0. And then we'd have our integral from t to 1 over the square root of x dx. So we can think about this area, finite or infinite, as the limit of this definite integral. Very similar to what we did with type 1s. Now we can actually figure out how to do this. So it would probably be helpful to recognize that this is the integral from t to 1 of x to the negative 1/2 dx. Then we can go ahead and integrate that, add 1 to the exponent, it's going to be 1/2, divide by the new exponent, we get the limit as t approaches 0 plus of 2x to the 1/2, evaluated from t to 1. Plug that in, we get the limit as t approaches 0 from the right of 2 times 1 to the 1/2 minus 2t to the 1/2. And that looks like we get the limit as t approaches 0 plus of 2 minus 2t to the 1/2. So now we want to apply this limit to here. Notice that this makes sense because t going to 0 from the plus side means that t is just barely positive, so we can't apply that square root. Square rooting something really close to 0 is also going to give us something very close to 0. So this is going to go to 2 because as t approaches 0 from the right-hand side, t to the 1/2 also approaches 0. So we get a value of 2, which means we did find a finite area. So in other words, this curve, we would say sort of from what we were discussing in the previous video, this curve collapses quickly enough to its vertical axis in this case, that the area in here, even though it gets infinitely tall, is so thin, the width is so infinitesimally small that this area is still finite. So this should tell you that even though a type 2 improper integral is very different because it's based around a vertical asymptote as opposed to a horizontal asymptote, the concept of changing it into a limit like we did here is exactly the same. So just like we did in the previous sort of investigation, let's go ahead and give a summary of the sort of official definition of these type 2 improper integrals. So a type 2 improper integral is a definite integral whose interval of integration involves a vertical asymptote, either at one of the endpoints, like it was here, in this case it was at the left endpoint, x equals 0, or of course it potentially in the middle of the interval. So you could have your vertical asymptote in the middle of the interval. So just like before, we rewrite these improper integrals as a limit of a definite integral. So every time we run into one of these, we're going to have to rewrite it as a limit of a definite integral. And once again, we're going to often use what is referenced as that sort of dummy variable or that parameter. So we have sort of 3 situations I'd like to mention here. So suppose we have f of x on an interval a to b. If the vertical asymptote occurs at x equals a, which is exactly what happened here, if it occurs at the left endpoint, then we will convert the integral from a to b f of x dx as the limit as our parameter t approaches a from the right, so a plus, for the integral t to b f of x dx. So notice what we're basically doing is we're replacing that a, since that's where the vertical asymptote occurs, with a limit as t approaches a from the right. If the vertical asymptote occurs at x equals b, meaning the right endpoint of the interval, then we will rewrite the improper integral, integral a to b f of x dx, as the limit as our parameter approaches b from the left, because obviously if you have this interval a to b, you're approaching b from the left, so b minus in limit notation, of a to t f of x dx. So once again, you sort of identify the trouble spot and you're going to replace that with your parameter. If you are unlucky enough that the vertical asymptote occurs at x equals c, which is inside the interval a to b, then what you're going to need to do is split your integral at that moment. So we would say that the integral from a to b is going to be that we're going to first approach the asymptote from the left-hand side. So as t approaches c from the left, a to c, so that's basically taking the place of a to c. And then this guy here takes the place of the integral from c to b. So we basically divide up, because the asymptote occurs in the middle of the interval, we basically go from a up to c, and then we go from c to b. So these two components handle it. Just like beforehand though, you need to use different parameters because these are 2 separate limits. And as we'll note down here, if one of these 2 pieces diverges, the overall improper integral is said to diverge. Just like beforehand, we use the same sort of language. So if the limit converges to a finite value, then the improper integral converges to that value. And geometrically, that means that there is a finite area under the curve on the interval we are studying. And we would say that the limit diverges, again, either by not existing or by approaching positive or negative infinity. Then we would say the corresponding improper integral diverges. And again, remember in case 3, where the asymptote would be in the middle, if one of these 2 pieces diverges, then you're already done. You can just say the overall integral diverges. Okay, now that we have this sort of definition and everything, let's take a look at a couple examples. So, for our first one here, we want to try to determine if the following improper integral converges or diverges, and again, if it converges, give the value. So we have the integral from 0 to pi over 16, secant squared of 8x dx. Now, the first thing you should recognize here is that spotting improper integrals of type 2 is a little bit trickier because there's no obvious infinity here, right? In type 1s, they have an infinity in those integration bounds, so you immediately know you're dealing with something that's improper. Here, that's sort of hidden. What's the improper issue here? Well, we can sort of identify that at pi over 16, if you plug pi over 16 into there, you get 8 times pi over 16, which is going to be pi over 2. What is secant squared at pi over 2? Well, secant squared is 1 over cosine squared, and cosine at pi over 2 is 0, so you get a divide by 0. So this is going to be the issue here. So we're going to need to rewrite this as the limit as t approaches pi over 16, and we'd be approaching pi over 16 from underneath since we're going from 0 to pi over 16. So pi over 16 minus there. And then we'd have our integral from 0 to t of that secant squared 8x dx. This should be pretty easy to do. We know that the integral of secant squared is tangent. This is a linear substitution, so we'll get an extra factor of 1/8. You could do it as a u sub, but I'm just going to do it in one line instead. So this will become 1/8 tangent of 8x evaluated from 0 to t. Let's plug that stuff in then. We get the limit as t approaches pi over 16 from the left. We get 1 over 8 tangent 8t minus 1 over 8, and then we get tangent of 0. Don't need to, but might not be a bad idea to just clean this up. Tangent of 0, of course, is 0, and we actually get the limit as t approaches pi over 16 from the left, 1 over 8 tangent 8t. Okay, so now we need to analyze this. So as t approaches pi over 16 from the left, this 8t is going to approach pi over 2 because we're multiplying this by 8. So if this gets really close to pi over 16, the argument in here will get really close to pi over 2. What happens to tangent at pi over 2? Well, if you think about the graph of tangent, you know that it sort of looks like this, and there's those asymptotes. One of them is at pi over 2. So since you're approaching from the left, this is going to grow towards infinity. So this is going to approach positive infinity. If we were approaching pi over 16 from above, then we would be on the other side. And remember that sort of tangent looks like this, and then it looks like this again. So if we were on the other side, we'd be going to negative infinity, but we know we're on this side, so we're actually going to positive infinity here. So that tells us that this is an improper integral of type 2 that diverges. So this is an example of a divergent type 2 improper integral. Notice, very similar to how we handle type 1s, always going to change it into the limit of a definite integral, perform the antiderivative, plug in the bounds, and then apply the limit. Okay, let's go ahead and take a look at another one. So we want to determine if this improper integral converges or diverges. So we have the integral 0 to 1, x squared ln x dx. Again, we need to figure out what the issue is. Well, there's not going to be any issues with x squared, but of course ln x does have some. You can't plug 0 into ln x, so the issue this time is going to be at that 0. So we're going to need to rewrite this as the limit as t approaches 0 from above, or from the right, because we're going from 0 to 1, so we're approaching 0 from numbers slightly above 0. The integral of t to 1, x squared ln x dx. So again, always first step, rewriting it as a limit. Now, this is probably a good one for integration by parts because we have a product. So we can do u to, and our dv. Again, we want to probably avoid having to integrate the ln, so we don't want to put the ln as the dv. So we'll put the ln as u and put the x squared dx as the dv. That means du is going to be 1 over x dx, and v is going to be 1/3 x cubed. So we're going to get a limit as t approaches 0 from the right. Big set of parentheses, we have our u and our v. So we get 1/3 x cubed ln x minus the integral of this v du. So that's 1/3 x cubed 1 over x dx. And then all of this is being evaluated from t to 1. Okay, let's go ahead and finish up that integral then. We have the limit as t goes to 0 from the right. 1/3 x cubed ln x minus the integral of 1/3 and x cubed and 1 over x. That's going to make it x squared d to the dx, evaluated from t to 1. We can now go ahead and do that. So limit as t approaches 0 from the right, 1/3 x cubed ln x minus integrating this is going to give us another 1/3. So we'll get minus 1/9 x cubed evaluated from t to 1. Now we can go ahead and pop in those bounds, that 1 in the t. So we get limit t goes to 0 plus. If we pop in the 1, we get 1/3 1 cubed ln of 1 minus 1/9 1 cubed. Parentheses around that, and then subtract what happens when you plug in t. Oh, excuse me there. 1/3 t cubed ln of t minus 1/9 t cubed. There we go. Now again, we could just go straight to applying the limit to this, but it probably doesn't hurt to simplify this a little bit, especially since this part just drops out, and it looks like we get the limit as t approaches 0 plus. Looks like we have minus 1/9, and then we have minus 1/3 t cubed ln of t plus 1/9 t cubed, once we actually sort of apply all that stuff. Okay, so let's go ahead and take a look at this then. Well, if we take the limit as t goes to 0 plus, this term should be nice and easy. This one right here, we know that this is going to approach 0. Because if you have t approaching 0 and you cube it, it's still going to approach 0, multiplied by 1/9, it's still going to approach 0. This one's going to be a bit more troublesome. Because here, if we look at this term, this piece is going to be going to 0, but this piece, ln, as you plug in things that approach 0, is going to approach negative infinity. And we're going to have an indeterminate form of 0 times negative infinity. So we're going to need to analyze this a little bit further. So let's go ahead and do that on sort of a separate page here. So we want to analyze in particular the limit as t goes to 0 plus, and we just need to worry about that one term, which was negative 1/3 t cubed ln of t. And like we said, the issue here is that this is really coming out as negative 1/3 times 0 times negative infinity. So we're in the indeterminate form here of a 0 times infinity. Unfortunately, 0 times infinity is not a situation where you can initially apply L'Hopital's rule. Instead, you need to move one of these terms into the denominator. Probably easier to do that with the t cubed, treating it as a t to the minus 3. So we're going to do this as limit t goes to 0 plus minus ln of t over 3t to the minus 3. Now, as t goes to 0 plus, up here, you're going to be going to negative infinity. And down here, you're going to 3, and then 0 to the minus 3, that's really 3 over t cubed. That's going to be going to positive infinity. So now you're in infinity over infinity case. So now we can go ahead and use L'Hopital. So limit t goes to 0 plus. We differentiate top and bottom separately. Negative 1 over t, negative 9t to the minus 4. We can simplify that. Let's swing this t to the minus 4 back up as a t to the 4th. And it looks like we get limit t goes to 0 plus t cubed over 9. Where is this headed? Well, as t goes to 0, now this is a t to a positive exponent. So this is headed to 0. So after all that, if we go back and grab what we originally had here. Okay, there we go. Bring this over here. After all that sort of work, we just figured out that this term here is also going to be going to 0. So this overall limit is going to be going to minus 1/9 plus 0 plus 0. So we get minus 1/9 overall, which means this is an example of a convergent type 2 improper integral. Big thing here was, once again, we had to make use of an integration technique to actually perform the integral, and we ran into an indeterminate form because of that 0 times negative infinity, so we had to analyze that part of the limit a little bit more carefully using L'Hopital's rule, but then we were ultimately able to show that this guy converges. Okay, let's take a look at one more example, sort of making sure that we understand how to do this when we have those sort of techniques of integration that we've covered. So we're going to try to do this one here, which is an improper integral from 1/2 to 1 of 1 over x squared root 1 minus x squared. Might not be initially clear where the issue is, but here we can see that the 1 is going to prove a problem, because trying to plug in 1 here is going to give us square root of 1 minus 1, which is square root of 0, which is 0, and we cannot divide by 0. So we're going to have to rewrite this as the limit as t approaches 1 from the left, because we're coming under 1. And then we have the integral 1/2 to t, 1 over x squared root 1 minus x squared dx. Okay, now we need to focus on actually integrating this. Unfortunately, this is going to be a pretty messy one because we've got that root 1 minus x squared in there, which means we might want to try to use trigonometric substitution. So let's try to do x equals sine theta. And we're choosing sine theta because we have 1 minus x squared. So if we plug in sine theta, we'll get 1 minus sine squared. And then we can use Pythagorean identity, say 1 minus sine squared is equal to cosine squared. Got to also handle the dx, so that'll be cosine theta d theta. We also should probably think about these bounds. So we had x going to be t, and then we'd like to think about the bound in terms of theta. Now, if x is t, we would have t equals sine of theta. The best we could say about theta then is theta is arc sine of t. So we'll carry this as an arc sine of t. And then for 1/2, well, that would give us from here 1/2 equals sine theta. When does sine of theta equal 1/2? Well, we could say arc sine of 1/2, but we can do a little bit better. We know that sine of theta equals 1/2 at pi over 6. So those will be our new bounds. Okay, so let's go ahead and pop all that stuff in there. We now have the limit as t approaches 1 from the left, the integral from pi over 6 to the arc sine of t. A little bit ugly with that arc sine of t, but that's okay. Then 1 over sine squared of theta, that's the x squared. Then square root 1 minus sine squared theta. And then that dx is now cosine theta d theta. So we can continue on. Limit t goes to 1 from the left. Integral pi over 6 arc sine of t. 1 over sine squared theta. And of course, the whole point of this is to use that Pythagorean identity and get that to square root cosine squared. It's cosine theta d theta. Then, of course, we can get rid of that radical. So we now have the limit as t approaches 1 from the left. Pi over 6 arc sine t. 1 over sine squared theta. Cosine theta d theta. Now we can go ahead and cancel those things. We have the limit as t approaches 1 from the left. Integral pi over 6 arc sine of t. 1 over sine squared d theta. Okay, now these steps here, from here all the way down to here, those are just standard trigonometric substitution steps. Use the Pythagorean identity, simplify the radical, cancel anything. Now here's a moment where you need to pause a little bit and think about how you want to proceed. Remember, we like products of sines and cosines and products of secants and tangents. So this, we don't really like the sign being in the denominator, so we can flip it up pretty easily. We can treat this as the limit as t approaches 1 from the left. Integral pi over 6 arc sine of t, and we get cosecant squared d theta. We might not be super thrilled seeing cosecants because we've spent most of our time talking about secants and tangents, but we actually know that except for a negative sign, this is exactly the derivative of cotangent. So we can just do a direct antiderivative here. We'll just bring this over to here. So we have the limit now as t approaches 1 from the left, and this is going to be negative cotangent of theta, evaluated from pi over 6 to arc sine of t. Do we need to undo the substitution? Well, no, because we changed our bound, so we can just plug in here, and we get the limit as t approaches 1 from the left of negative cotangent of arc sine of t, and then plus cotangent of pi over 6. So if we want, we can start by thinking about what cotangent of pi over 6 is. That would be cosine of pi over 6 divided by sine of pi over 6, which would be root 3 over 2 divided by 1/2. So this is going to be root 3. So we have the limit as t approaches 1 from the left, negative cotangent of arc sine of t, plus, we said that this is going to be root 3. Now we need to analyze this component. So this is a composite limit, so it might be a little bit tricky, but just keep in mind this limit is going to apply to here first. So as t approaches 1 from the left, what happens with arcsine? So remember what arcsine does? It tries to give you the angle that outputs this in here. So what angle outputs things really, really close to 1? Well, this would be approaching pi over 2. Since it's slightly under pi over 2, we could say that this is approaching negative cotangent of pi over 2, also from the left, plus root 3. Now, since we're approaching pi over 2 from the left here, well, remember cotangent. We can think about this as sort of negative cosine of pi over 2 from the left over sine of pi over 2 from the left. Again, there's technically like a little limit here, but that's okay. Plus root 3. And of course, up here, that's going to go to 0. Down here, that's approaching 1. 0 over 1, well, that's actually nothing bad. That's just 0. So this approaches 0 plus root 3. So this means that this approaches root 3. So we found another one that converges here. This is another example of an improper integral that converges. All right, so what's sort of interesting about this one, of course, is just the fact that we had to use that trigonometric substitution, and we also changed our bounds, making sure that we're comfortable doing that even in a situation where we have an improper integral like this. All right, let's turn to our very last example of this, one that is a very sort of sneaky one. So let's take a look at our last example here. For this one, we have the integral from 2 to 8 of 5 over 2x minus 14. Why is this a sneaky example? Well, if you look at this, if you didn't read the question and see mention of improper integral, you might look at this and say, well, plugging in 8's not an issue, plugging in 2's not an issue, you don't get any divide by zeros, so I can just integrate this and plug in the bounds. If you do that, everything's going to turn out incorrect there. The reason is you have to recognize that the problem is giving you a hint. It's saying that it's an improper integral, so there is some issue with this. The problem is that the issue is not at the two ends, it's actually in between. The issue is when 2x minus 14 is equal to 0, which happens when 2x equals 14, which happens when x is 7. So we're going to have to split this up as two pieces. We're going to have to think about this as the integral from 2 to 7 of 5 over 2x minus 14 dx, plus the integral from 7 to 8 of 5 over 2x minus 14 dx. Now, each of these is their own improper, so this one we can think about as the limit as t approaches 7 from underneath, 2 to t, 5 over 2x minus 14 dx, plus the limit, use a different parameter, r going to 7 from above, integral r to 8, 5 over 2x minus 14 dx. Gotta view it this way. You gotta recognize that there is an issue here. Yeah, it's not at the two ends, it's in the middle. So we need to split it at that point where the vertical asymptote actually exists, where we're getting that divide by 0. Now choose one of these to start with. So let's just let's choose the second one, just for fun. Limit r going to 7 plus, integral r to 8, f or 5 over 2x minus 14 dx. This should be very easy, right? This is a linear substitution. If we did that, we would get u equals 2x minus 14. So we'll get an extra factor of 1/2. So we should be able to do that in sort of one line. Limit is, r approaches 7 plus. We should get 5/2 ln 2x absolute value 2x minus 14 evaluated from r to 8. Why are we getting 5/2 there again? Because you have that linear substitution. Derivative of 2x minus 14 is 2, so we get a reciprocal of that out front. Now we can plug in, and we get that we have the limit as r approaches 7 plus of 5/2 ln, plug in the 8, I guess you get ln of 2 minus 5/2 ln absolute value 2r minus 14. So what's going to happen here? Well, as r approaches 7 from above, in here, that's going to approach 14 minus 14. So you're going to approach 0, again, slightly from above. So this is going to tend towards 5/2 ln of 2 minus 5/2 ln 0 plus. That's sort of what it's going to resemble in there. What happens in ln of 0 plus? Well, this is what ln looks like. If you're doing 0 plus, you're sort of tracing down there. This is going to go towards negative infinity. So this is going to approach 5 halves ln of 2 minus 5 halves times negative infinity, which means that this overall thing is going to approach positive infinity. We don't really care where it approaches. We just know that this piece diverges. So what does that tell us about the overall thing? Well, we don't even need to bother analyzing the other piece. The whole thing diverges as well. So the whole improper integral diverges. Does that mean that the whole improper integral also diverges towards positive infinity? Not at all. We just know this piece goes to positive infinity, and that tells us that the overall thing simply diverges. We don't know where it's headed. Maybe it doesn't exist. Maybe it does go to positive infinity. Maybe it actually turns out that the overall thing goes to negative infinity. Who knows, right? We just know that it overall diverges. So, if you combine what we've just done in this video with the previous one, you now should feel very comfortable sort of analyzing and working with type 1 and type 2 improper integrals. In our next video, we'll finish up section 7.8 by talking about a way of sort of analyzing improper integrals without actually having to do the entire calculation. So we'll talk briefly about what is called the comparison test for improper integrals in our next video.